Welcome to today's explainer. We're jumping right into one of the most fascinating and honestly most misunderstood challenges in all of tech right now. We are talking about the hard, physical constraints of AI hardware scaling. We all see these massive new AI models writing code, passing the bar exam, generating crazy videos, and the natural assumption is just, well, we must have built faster calculators, right? But the physical reality of what is actually holding artificial intelligence back right now is entirely different. And frankly, it's a lot more interesting. Okay, let's dive into this. Is AI scaling really limited by raw compute power? Are we just sitting around waiting for chips that can push more flops, floating point operations per second? This is the massive misconception surrounding AI performance limits. We tend to picture these chips just grinding away, absolutely maxed out on math, sweating to calculate the sheer volume of data in a massive transformer model. But if you were to actually look inside the processor during a training run, you wouldn't see a chip choking on too much math. No, you would see a chip that is essentially a hungry monster, completely starved for data. This totally flips the script. The hard reality is that data movement, not math speed, is what truly chokes transformer models. These incredibly advanced hyperfast compute units are constantly just sitting there, completely idle. They're just twiddling their thumbs, waiting for weights and activations to arrive from the memory banks. It's literally a feeding problem. And that brings us to a concept known as the memory wall. Basically, this is the growing performance gap between how fast we can compute data and how fast we can actually supply that data to the compute units. In AI hardware, compute speed, the flops, has scaled up incredibly fast. But the bandwidth, meaning the absolute sheer volume of data you can move per second from the high bandwidth memory, or HBM, into the cache and to the cores, well, that's lagged way behind. The result? A massive bottleneck where computation is entirely choked out by data movement. So why does this wall even exist? Well, we have to look at the physical reality of chip design. It's transistors versus wires. See, compute scales with transistor density. We can shrink transistors, we can pack billions of them on a die, we can even stack them in 3D to crank up our compute power. But memory bandwidth? That relies on physical wires, pins, and interconnects. And you just cannot shrink wires the way you shrink transistors. Bandwidth is bottlenecked by strict packaging constraints, the physical routing on the substrate, and signal integrity. You simply can't pack infinite physical wires onto a chip package to move all that data. And here is a truly staggering number. Moving a piece of data from the high bandwidth memory costs 100 to 1,000 times more energy than actually performing a calculation with it. Think about that for a second. The energy cost of just moving bits around completely dominates the system. Even if you could somehow magically fit more wires to increase bandwidth, the sheer amount of simultaneous signaling required would cause a massive explosion in power consumption and heat. Physics literally puts a hard ceiling on how much data we can shove around a circuit board. Moving on to Section 1, the architectural divide between GPU and TPU. So how do we solve this data movement problem? The tech industry has basically split into two distinct hardware architectures, both designed to attack this exact same memory constraint, but from totally different angles. Let's introduce our two protagonists. First, the GPU, or Graphics Processing Unit. Originally for rendering graphics, repurposed for AI. It is essentially a highly programmable, massively parallel computer. It thrives on flexibility, using dynamic thread scheduling to juggle thousands of tasks. Think of it like a highly efficient city traffic grid. On the other side, we have the TPU, or Tensor Processing Unit. This is a fixed tensor factory. It uses a continuous data flow path specifically engineered for dense linear algebra. So less like a traffic grid and much more like a rigid, hyper-optimized assembly line. Now, what's really interesting about this comparison is how these two trade off against one another. Take a look at flexibility. GPUs are very high there, making them the absolute king for research, dynamic architectures, and just general AI workloads. TPUs are low on flexibility, but extremely fast at dense matrix operations. And notice the software side too. GPUs lean on the super mature CUDA ecosystem, while TPUs are highly dependent on their XLA compiler. With TPUs, the performance actually comes heavily from the compiler, optimizing that assembly line ahead of time, rather than manual tuning on the fly. But let's look a bit closer at why the GPU's flexible approach can actually be a liability for large-scale AI. When a GPU breaks a massive matrix multiplication down, it relies heavily on thread blocks, shared memory, and caching. And all this dynamic scheduling creates overhead. Every single time it launches a kernel, which is just a tiny chunk of work, it has to manage synchronization. If you have small batch sizes or irregular data shapes, the GPU struggles to keep all its arithmetic units busy, leading to massive underutilization. It's incredibly versatile, for sure, but that versatility brings scheduling fragmentation that just eats up precious time and memory bandwidth.
So how does the TPU avoid this trap? It uses what's called a systolic array data flow. Instead of juggling a million threads, it just streams data directly into a fixed compute fabric, basically a massive grid of multiply accumulate units. As the data flows through, each unit computes partial sums and accumulates them locally. And step 3 is where the magic happens. It propagates those results directly to the next unit without ever writing back to the main memory. It keeps the data moving entirely within the compute array, drastically minimizing those incredibly expensive round trips to the HBM we talked about earlier.
This design fundamentally shifts the paradigm. As the source material beautifully summarizes, it's about turning matrix multiplication from a cache and scheduler-heavy operation into a continuous data flow problem. By eliminating all that instruction overhead and maximizing data reuse inside the hardware itself, the TPU ensures its arithmetic units stay busy almost every single cycle. It achieves a much higher percentage of its theoretical maximum flops because it's not waiting at traffic lights. It's just a relentless conveyor belt of math.
So, the crucial point is that while TPUs are incredible at hiding the memory wall during matrix math, they do not erase the laws of physics. They still face fundamental limits. A TPU model size is still hard-bounded by the physical capacity of the HBM. It also doesn't fix the quadratic scaling problem of attention mechanisms and transformers, it just executes it more efficiently. Plus, TPUs are rigid. They still rely on CPU or GPU-like logic for nonlinear operations and control flow inefficiencies, like GLU or layer norm, the complex math that helps the AI actually learn. They are highly specialized factories, not universal solutions.
All right, let's look at Section 2, the photonic frontier, hype versus reality. Which brings us to the horizon. If pushing electrons around silicon is hitting a physical limit of heat and bandwidth, what about moving photons instead? Light. There is a ton of confusion in the industry here, so we need to draw a really clear line between two totally distinct technologies. On one side, we have optical interconnects. This is using silicon photonics, basically tiny fiber optics, purely for moving data between chips and memory. This is mature, it's widely deployed in data centers today, and it dramatically improves bandwidth and energy over distance. On the other side, though, we have photonic accelerators. This is the experimental stuff. This is using light interference itself to actually perform the matrix math. And this brilliantly illustrates why the experimental side is so incredibly exciting. Because if we can compute with light, the physics are entirely in our favor. By encoding values into the amplitude or phase of light and passing it through beam splitters, the actual multiplication happens with near zero marginal energy. The physics of the light just does the math for you. You also get massive parallelism because you can use the superposition of different light modes all at the exact same time. It offers gigahertz signaling speeds and produces a tiny fraction of the heat compared to billions of standard transistors aggressively switching on and off. But we have to ground the hype. Why aren't we all using optical chips right now? Well, because light has very realistic limitations. The biggest one? Optics are naturally linear. But neural networks desperately need nonlinear functions, like ReLU, which is a critical learning function, to learn complex patterns. Light can't do that natively, so you still have to hand the data back to standard electronics. On top of that, we don't have optical memory yet, so you are still tethered to standard electronic memory like SRAM and HBM. And constantly converting signals from electrical to optical and back again introduces an overhead that can completely erase all your energy gains. Not to mention the immense physical complexity of routing light accurately on a tiny chip without phase drift or noise messing everything up. Let's move to and see how this builds a realistic vision of our hardware future. The answer isn't that optical chips are just going to completely replace GPUs. The real answer is a hybrid architecture. In the near future, we will very likely see standard electronic GPUs handling the memory, the control flow, and all those tricky nonlinearities. Attached directly to them will be specialized optical engine coprocessors, acting purely as hyper-efficient accelerators meant to just crunch through massive linear algebra matrix multiplications with zero heat. It's really about combining the flexibility of electrons with the insane bandwidth and speed of photons. So that leaves us with one final massive question to consider. As AI models continue to scale exponentially, demanding ever larger matrices and deeper attention networks, what happens next? Will brilliant architectural innovations like hybrid optical electronic coprocessors and crazy advanced 3D packaging allow us to invent our way around these physical interconnect limits? Or Will the stubborn, unyielding physics of moving data around a board eventually serve as the ultimate hard ceiling on the development of artificial intelligence? It's quite literally the most critical engineering race of our time, and the solution will shape the entire future of computing. Thanks for joining me on this explainer, and I'll see you in the next one.